as I said, Monday, hopefully you watch the average rate of change video like I asked. Otherwise, we'll just go over it briefly and see what's going on in the PowerPoint. So basically, the average rate of change is fundamentally kind of like trying to understand how a function is behaving in a short window of time, right? So the whole point is kind of like we understand linear functions very well, and over a short time frame, you can model things linearly. So I'll write down the definition, but then we'll have a look at the picture. So the average rate of change of f of x from x equals a to x equals b is given by, and sometimes I'll just abbreviate it ARC like this. It's f of b minus f of a over b minus a, which is essentially just the the slope formula. You're changing y over you're changing x. The only reason it's a little bit different is normally your function is going to have a formula that you're going to plug things into. So you have some picture where you might have some function doing something. Maybe it's, I don't know, maybe it's something like this. And this is giving the slope. And this point here would be like your f of b, your height, or your f of a and your f of b, right? Basically, this point has coordinates a, comma, f of a. And this point has coordinates b, comma, f of b. So you're basically just doing the slope between those 2 points because you say, well, between those 2 points, this is behaving pretty linearly, right? Outside there, it's the line is not going to be such a good model, but for that small time span, if I want to do some interpolation, I can go ahead and maybe use that line to understand how things are changing. This kind of reminds me of, a couple of years ago, people were talking about like, flat Earth on the internet and stuff like that. And like really, in some sense, it's almost like a magnitude issue. The thing is, if you can look at any shape with curvature, and so long as you zoom in enough, eventually it's going to end up looking like a line to your eyes. The same thing with like pixels on a TV. There's so many small pixels. Eventually, all these things that are really just a bunch of tiny little rectangles that can only show a few different colors of lights. They trick our eyes into thinking that we're actually viewing some sort of like continuous motion and some type of shaped curvature, when really it would kind of in its true sense be a bunch of jagged little lines. Yeah, so let's go ahead and just do an example where maybe and then the units here, just one note, is the units of the average rate of change are going to be a ratio of units like they are for the slope. So the units of the ARC are units of y, or units of your output, per your units of x. Okay, so let's go ahead and just do an example real quick, and then we'll look at the PowerPoint and see if that has anything interesting to offer. So find the average rate of change of f of x equals 8 natural log of x minus 3 from x equals 2 to x equals 7. So what we have to do is just find our y coordinates first. So let's say f of 7 is 8 natural log of 7 minus 3, and f of 2 is 8 natural log of 2 minus 3. So our average rate of change is 8 natural log of 7 minus 3 minus, and then parentheses since there's two terms, 8 natural log of 2 minus 3 divided by 7 minus 2. So you end up with 8 natural log of 7 minus 3 minus 8 natural log of 2 plus 3 from distributing that negative sign over 5. So the plus 3 and the minus 3 are going to drop out. So we have 8 natural log of 7 minus 8 natural log of 2 over 5. Let's go ahead and punch that in the calculator and just get an approximation. So it's about 2.00. So it came out to a pretty nice value. So that's basically it. There's not too much to computing an average rate of change. As I said, let's go ahead and take a look at the PowerPoint and see if that has anything to offer. So let's see. So probably can get to it from this folder. Yeah. So we are in section 2.1. I don't rename it. Yeah, so this chapter is the derivative. So really one thing to think about is the derivative is going to come from this average rate of change. This is why we're thinking about it. If we combine the average rate of change with the notion of a limit, this is what's going to give us the derivative. So kind of the components of section 2.1 average rate of change and 2.2 limits are what gives us the tools to understand the derivative. Okay. So again, talking about how things change, the average rate of change. We've got our delta x and delta y, and if you take that ratio, you get the average rate of change. So f of x2 minus f of x1. I use b and a. It doesn't matter what you call your endpoints on your interval. Okay, so they go over an example here where they have 4t squared minus 3t. Again, what they want to do is they want to do g of 5 minus g of 2 over 5 minus 2. They computed them right here. So what they did is you just plug 5 in. 4 times 5 squared minus 3 times 5 is giving you 85. And 4 times 2 squared minus 3 times 2 is giving you 10. So basically that you're going to end up with 85 minus 10 divided by 3, which will be 25. So that's the average rate of change for this problem. Okay, the geometric thing, again, we get the picture and we have some curve and we basically have just the line going through those 2 points. So we're essentially calculating the slope of that red line there. They just call it a secant line. Secant is Latin, just meaning cut. So it's just cutting across those 2 points. It's kind of like you're chopping off a small section of the curve and looking at the line that connects the two dots. But yeah. Okay, again, it's the slope of that line, which we already saw. This one, so here we have an example where they're showing us a graph and maybe they ask us for an average rate of change from the graph. So that's all we do is we'd figure out what the 2 points are and then connect those dots and use the slope formula to figure that out. More interesting, though, to me is what are the units going to be here? Because, again, remember the units of an average rate of change are going to be units of a slope. So your Y value units here is fuel economy in miles per gallon, and your speed is the input unit in miles per hour. So if you do miles per gallon divided by miles per hour, that would be the units of your average rate of change here. So if we take a look at that, say we have miles per gallon divided by miles per hour, that would be the same thing as miles per gallon times hours over miles. So your miles would cancel. So what your units here are hours per gallon. So it's essentially telling you how long you can drive or how long the average person in the scenario can drive on a gallon of gas. So that's pretty interesting there. It's giving you some notion of efficiency based on time. So that's interesting to think about. So hours per gallon would be your units of the average rate of change. So they say estimate the average rate of change of fuel economy when driving speed increases from 45 to 70. So 45, you would find your point up here. I don't know, maybe that's something like 28. You'd have to estimate that. And when you get to 70, maybe it's more like 24. I would say 28 and 24. Again, this graph is not super precise, so it's kind of hard to exactly know what values. Let's see what they say. I'm saying 28 and 24. They're just saying the decrease is 5. They're saying you're dropping 5. With mine 28 to 24, I would have been guessing 4. So we're seeing maybe 1 unit difference. But I mean, from a graph, again, it's without more tick marks, it's hard to know exactly how much. But the 25 we know for sure because they give us the x values 45 and 70. So if you do 70 minus 45, you get exactly 25. So our delta x is pretty precise. Our delta y is kind of estimated using the graph. And so they get the slope negative 5 over 25. And then here they talk about the units. Yeah, they didn't interpret them very well in terms of this. They're saying for each 0.2 miles per gallon, it's, increase in driving speed. If you think of that as minus 0.2, that would be minus 0.2 hours per gallon. So we could interpret it that way. Basically, you'd get 2/10 of an hour. So a tenth of an hour is 6 minutes. So 2/10 would be 12 minutes, right? 20 an hour. So basically, this is telling you by increasing your speed, you're getting 12 minutes less per gallon of gas. That's another way to interpret it. 12 minutes less driving time per each gallon of gas. Of course, the trade-off is you're getting there faster. So okay, so shrinking the interval, this is going to be the idea. And it's really the same idea. Like I mentioned, you can zoom in on any curve enough and you'll end up getting something that looks like a line. Why don't we just see that on Desmos real quick? So I've got a graphing calculator up here, desmos.com. Let's say we want to graph a circle. So we've got goes out to about 6. Why don't we make it a circle with 4? So x squared with radius 4 plus y squared equals 4. It's the square root, so 16. Yeah. So we have some circle. We can zoom in on this, and eventually we can get a section that just looks like a line. So say we focus here, and we just want to move, and we could probably just zoom in. And as we do it enough, you can already tell. Eventually, this thing looks pretty darn straight. Right? So if you're looking at this from this angle, you might say, well, gosh, it's a straight line. But if you zoom out, it turns out it's actually just a circle. So as you shrink the interval, this average rate of change is going to produce a graph that better and better and better models whatever you're trying to look at. So this is the idea of the derivative. Kind of if you zoom in on anything long enough, you're going to get something that's essentially pretty straight. As long as it's got to be a kind of a smooth function. Okay, so shrinking the interval. You can compute it over any interval, large or small, but The smaller intervals are going to give you a better idea how they're changing near a particular point. Yeah, so the next example, we're going to look at a dropped ball. So this is pretty common if you've had any physics. These are just modeled very well using the Newtonian equations of motion, and the primary driver is acceleration from gravity on Earth. So that's minus 32 feet per second if you're measuring in English units. If you're in the metric, it would be minus 9.8 meters per second squared. So, okay, suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Estimate the speed of the ball after 5 seconds. I think there was a picture at the beginning. I think it was actually this tower of this section. No, maybe that's in the textbook. I must be thinking of the textbook. I think there's a picture of it. I've never been to Toronto, so I don't know this tower. Okay, so through experiments carried out 4 centuries ago, these would have been Isaac Newton, Newtonian mechanics. Oh, Galileo had these as well. Okay, well, Newton wrote down a lot of the equations, but then he also showed that they could be derived via calculus as well, which he's one of the co-inventors. But he discovered that the distance fallen by any freely falling body is proportional to the square of time it's been falling, and this neglects for air resistance. Right, so this was one of the famous things that they said. All these people that thought Galileo's ideas were bad. They would show examples of things that would drop in different time intervals. The common one was a hammer and a feather, so he would drop a hammer. They would drop a hammer and a feather, and the feather obviously is much more impacted by wind resistance. So they fall at different speeds, but he said, well, if you would do this in a vacuum, they would actually fall at exactly the same rate. And so one of the trips to the moon, they actually brought a hammer and a feather, and they dropped them, and they hit the ground at the same time exactly. So kind of validated those experiments. Okay, so Galileo's law is expressed by this equation: S of t equals 4.9 times t squared. If we compute the average rate of change, we're finding an average speed. The difficulty in finding the speed at precisely 5 seconds is that we're dealing with a single instant of time. Yeah, so since you've got a single instant of time, it's hard to do. So what you do normally is you pick some small interval, like 0.01 seconds. So maybe what we would do is use the average rate of change from 5.01 to 4.99, and you're just 0.01 on either side of the interval, and doing that. That would give us a good approximation of the speed, because it wouldn't change much around those points. Okay, so they're doing 5 to 5.1. The only reason I don't like that is 5 is not the middle number. I would rather them do 4.9 to 5.1. But okay, you get the idea. They're using some interval about 5. That's very small, 0.1 seconds. So we're using that function 4.9 times t squared. So we've got 5.1 and 5. We're plugging it on top. So that's why we have 5.9 times 5.1 squared minus 4.9 times 5 squared. And 5.1 minus 5 just gives us 0.1. So doing that says after 5 seconds, that ball should be traveling around 49.49 meters per second. And then they do it over a bunch of smaller and smaller intervals. And you can see it's less accurate going from 5 to 6, but eventually these things start to it looks like they converge as we get smaller and smaller along the interval to about 49. So if you ran this experiment a bunch of times, and again, this would be something that would be easy to compute on Excel. Yeah, that the actual speed would be more like 49 meters per second. Okay. Yeah, so they're just talking about how this leads to the idea of a limit. We see that it's approaching something. It's like an asymptote. It's getting closer and closer and closer to that number. And mathematically, the way we talk about that is using the limit. So mostly in this class, we're going to talk about the limit graphically, but we will talk about it algebraically some. But the very precise notion, you have to use epsilons and deltas, and it's a little bit confusing. So we won't be doing that, but we'll still have a good idea of how these things work. Um, just give me 1 second. I was just checking for something here. Yeah, so if you've never seen it before, I just wanted to show you maybe that moon thing that I was talking about with the hammer and the feather from the Galileo experiment. So why don't we have a look and see? Let's just type in hammer, feather, moon, and we can see the picture here.
I just customized and saved with Liberty Mutual.
Ad, unfortunately.
What a great day. What an okay day.
Cam, we copied both Solar Wind and penetrometer drum in the ETB.
Just down a bit.
Not quite yet. I haven't put the Solar Wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time.
There you
How
go.
about that? Proves that Mr. Galileo was correct in his findings.
So I don't know if you've never seen that before. That's pretty cool from the Apollo 15 moon landing. Any questions so far in the chat? No. Okay. Let's go ahead and take a look at the 2.2 PowerPoint, where we start to talk about limits, and then we'll do some of that in class on Friday. Yeah, and at the end of class here, I'll check the homework. The homework date might need to be adjusted. Okay, so now we start to talk about the concept of limits. Okay, so this is talking about something that gets very, very close to something, how it's behaving, what it would tend toward, even if it might not exist there. So they're going to start by looking at this function x squared minus 1, or x minus 1 divided by x squared minus 1. So the thing is, this function is not actually defined at the x value 1. Why is that? Well, if you tried to plug 1 directly into this function, you'd end up getting something that's 0 over 0, which doesn't make sense, right? Division by 0 is undefined. But a limit doesn't really care about if the function is defined at the limit. It just cares about what was it really tending towards as it neared the value. So how can we look at that? Well, they're doing it with a table. Maybe we can do it by looking at a graph. The table's not very intuitive, but graphs tend to be intuitive. So let's go ahead and graph that function. So let's say we have, again, probably I want to reset this to a reasonable window. Let's say, I don't know, -8 to 8. 5 from -8 to 8. That looks so distorted. I don't know. That's weird. Probably just because the portion of the screen is not rectangular. Somehow this looks distorted, right? The scale looks wrong. This should look like a circle. Does it have my step? That's weird. I'm just going to refresh because I can't get this right. Okay. So let's say we have y equals, and then we had that function there, x minus 1 divided by x squared minus 1. So this actually doesn't exist at 1. So Desmos is graphing this by plugging in a bunch of points like they're doing, but really, in all manner of fact, you would have a hole in this graph. So this graph, the picture would really look more like the part of the picture we're concerned with would look something like, okay, so we've got something behaving like this. Really what's going on is there would actually be a hole here, an open dot where nothing exists there. But the graphing calculator doesn't realize that because it's just graphing in a bunch of points around it. So we can actually hover on that graph to figure out exactly what that is. So notice 0.99, it's near 0.503. So it's pretty close to 1/2 at that point. Essentially, why is that the case? Well, if you look at y equals x minus 1 over x squared minus 1, what you're going to get is you're going to get, you can simplify this by factoring, right? The bottom is a difference of squares. You can do x minus 1 times x plus 1. These cancel, and you end up with just 1 over x plus 1. So what this graph really looks like is it looks like 1 over x plus 1, which is your y equals x graph shifted 1 unit left. So 1 unit left would be here. That's your asymptote. So we have essentially the graph doing this on this part and this on this part, but it's not perfect. It's like y equals 1 over x plus 1 with a hole at 1, at your x value 1, because the original graph can't exist there. So these graphs are completely identical in every sense, except for there's a hole at that one point. And so that's what the limit's telling us. It's telling us, well, if we were moving along that curve, what would we expect to happen? If we knew everything about the curve except for we didn't know what happened at that point, well, we'd expect it to exist at 1/1/2, but it just has this oddity where there's a removable discontinuity. So, I mean, you see the same thing here. They're moving to 1, and we see all the y values getting closer and closer to 0.5 from both sides, coming from above as we move from the left, and as we move from the right, coming from below, meaning the values were bigger than 0.5 and they're getting closer and closer. And on the other side, they were less than 0.5, getting closer and closer. So we have some notation here. This limit notation, you're talking about what the x value is traveling toward and what function you're talking about. So that's the notation there. And if we have the point that we know it's moving towards, we can say it exactly equals that value. So a lot of times in general, you'll see this notation. You'll have the limit as f of x, or excuse me, I meant to say as x approaches a, of f of x equals L for the limit value is written with notation say as the limit as x approaches a of f of x equals L. So that's what we had in the examples there. The limit, we were looking at x moving toward 1. The function was x minus 1 over x squared minus 1, and we hypothesized it was moving toward 0.5. So, yeah, let's go ahead and move on. Okay, so there's the definition that we just wrote down, same thing. Sometimes they'll do it with arrows in two components. Your y values are moving toward L as your x values are moving toward A, which is what they say. The arrows you can just read as approaches. Okay, so estimating the limit of a function here. They're doing the same thing here. Again, we could do it graphically. So this is talking about the algebra of the limits, which we'll get into. What we have here is known as a difference quotient, which is really what's going to be happening when we're computing the derivatives. And there's a bunch of tricks for doing that. So I'm going to kind of gloss over this for now. We can see from the tables that it looks like the limit is moving toward 6. So you can get that by just plugging in a bunch of different values. You can also graph it and see what it moves towards as we go to 0. So let's think about this function 3 plus r squared minus 9 over r. Let's see if the graph is any better here. So the top was, I'm going to use x instead of r, 3 plus x quantity squared minus 9 divided by x. And we see it looks like this line, well, at least from this perspective. It's essentially a line, and we see it's hitting the y-axis, which is x equals 0 at 6. So that's another way to kind of confirm that's what's going on there, just by graphing it. So they're using the limit notation there. Okay, so they're not getting into the algebra. That's good, good. We just want to look at, so we have some limit laws. Again, they behave very nicely with all the things we expect them to. You can add limits of two functions. You can subtract limits of two functions. You can multiply by a constant. It's also multiplicative and divisible so long as your limit of g of x is not approaching 0 at that point. So we have those laws there. Okay, they're just writing them in words. And then there's also a power law. We're not going to. Okay, so the limit laws here, if you have a function basically, and so long as basically if you don't have any of those discontinuities, things like dividing by 0 or something like that, you can just plug in the number to evaluate the limit. So if you have a continuous function, meaning the function can be written without picking your pencil up off the paper, then you can go ahead and evaluate a limit by just plugging things in. So it works with your continuous functions. What are examples of continuous functions? Well, all polynomials are continuous, so that's a big class of functions. So polynomials, if we ever have a limit, we can just plug the number in. The example we see here is such an example. F of x is 2x squared minus 3x plus 4. So essentially to do this limit, you can just plug in your 5 for x's. So you'd have 2 times 5 squared minus 3 times 5 plus 4. So you'd have 39 is your answer. What about exponential functions? Those are continuous on their domain. Same with logarithmic functions. But things like rational functions, once you start taking ratios of polynomials, those are not examples of continuous functions. So they have lots of gaps. Okay, so they're just doing each term separately. So they're going to have a 50 minus a 15 plus a 4. So that's what you see it then, 50 minus 15 plus 4, which is 39. But we're not going to be involving ourselves too much with all of these limit laws. Mostly what we're moving towards is understanding the difference quotient, which will be in the derivative section. So continuity, we just talked about that. Continuous means you can draw it without picking up your pencil off the paper. It also means if you have a limit, that's all you have to do is plug in the value. So that's what this is saying right here. The definition of continuity via the limit says if you have the limit and it's the same thing as just plugging the number into the function, that the function is continuous there. So pretty easy to think about. If the thing that the limit approaches always exists at the point, then it's continuous. Another way to think about it. So you can talk about continuity at a point. If you say a function is continuous, that means it's continuous on its domain. If you talk about an interval, it would mean it's continuous at every point on that interval. So again, the graph we see down below, it's got a bunch of continuous segments, but it's discontinuous at two very clear places. It's discontinuous at -1 because you would have to pick up your pencil to jump from the open dot to the shaded dot. And then since you have like an asymptote at x equals 2, you have to draw that in two segments. So basically to draw this graph, you would have to pick up your pencil 2 times. So that means that this function is not continuous. Somehow I got onto the... Okay, so examples of the continuous functions, lots of classes of functions. Linear functions, which are polynomials. The following types of functions are continuous at every number in their domains. Is this a question or a statement? Because rational functions certainly are not. Oh, in their domain. See, that's confusing. So in their domain, it's true rational functions, but rational functions also certainly have discontinuities from the perspective. So what's an example? Like y equals 1 over x is certainly a rational function. So it's continuous at every point in its domain, but the point is 0 is not in its domain. So it's continuous for this part and continuous on that part, but the function has discontinuities over the real numbers. But the real numbers are not its domain, so a little confusing how they listed it that way. Anyhow, so yeah, this is what they're saying. With continuous functions, we can evaluate by doing direct substitution, which basically means you can just plug in the points, plug in your numbers to replace x. So pretty straightforward. So see, this here is a rational function, and when we want to find the limit at 1, that's not in its domain, but you can still actually talk about the limit there, right? The limit of this function is every number except positive and -1, because if you plug in +1 or -1, they both make the denominator 0. So as we see, plus and -1, those numbers are not the domain. All real numbers except 1 and -1. It's rational, so that means it's going to be continuous every point except those 2 points, 1 and -1. So if you are given a limit and the limit is x approaching any number other than 1 or -1, we can just say, okay, well, it's continuous on that section, so we can just plug in those values. So for part B here, they want us to do the limit as x approaches 4, which means we can just replace x by 4. So we get 4 minus 1 over 4 squared minus 1, so we get 3 over 15, or 1/5. But for 1, we had to do something different, right? We already did this. We factored the denominator, and we saw that we could go ahead and cancel that out. So the x minus 1s will cancel, and we'll get 1 over x plus 1. And then when you have 1 over x plus 1, you can actually evaluate the limit there because you don't have that problem 1 minus 1 in the denominator anymore. So once you've used the algebra to cancel out the x minus 1s, you can just go ahead and plug in 1 for x. So you'll end up with 1 over 1 plus 1, or 1/2. So that is the limit of that function, which we already saw via a graph and via a table. Okay. Here, do we have a problem? Yes, we do have a problem because if you try to plug in the limit directly, we see it's not going to work, right? 0 squared would be a problem. We'd be dividing by 0. So we use a trick here called rationalizing a numerator. Basically, the trick is to multiply by the conjugate. So this might be familiar to you from arithmetic. In arithmetic, we usually rationalize the denominator. So remember the main thing here, multiply by the conjugate. Is essentially the difference of squares, right? It says if you have an a plus b and you multiply it by an a minus b, you end up with just a squared minus b squared. So if you have two terms and one of them happens to be a square root, you can still get rid of the square roots, because if you multiply by the conjugate, you end up with a product or two terms where everything is squared. So let's just do a quick example from arithmetic. So back then we would rationalize the denominator. So we might have something like 5 over the square root of 17 plus 2. So to rationalize the denominator, you just multiply by the conjugate on top and bottom, because you can't change the expression, so you have to multiply by something equal to 1. So that something would be the conjugate of the denominator, which is the square root of 17 minus 2. So on top, you would just have this 5 times square root of 17 minus 2. And on bottom, what would happen? Well, you would multiply a plus b times a minus b. So you'd get the square root of 17 squared minus 2 squared. So on the bottom, what are we getting? We're getting 17 minus 4, which gives us 13. And on top, we get 5 square root 17 minus 10, distributing the 5. So notice we took an expression where the square roots were in the denominator, and we've written an equivalent expression where there are no square roots in the denominator. That's why they would say rationalize the denominator. For this example, what we want to do is we want to rationalize the numerator. So we would be multiplying by the conjugate of this guy on top. So we're going to end up multiplying by the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. And the reason is we're hoping that we can cancel out this t squared, so we no longer have that problem of plugging a 0 in and getting division by 0. So they do that here. We notice we're multiplying by the conjugate that we talked about. So on top, we're going to get this thing. Notice it would be the square root squared. The square root of t squared plus 9 squared would just be t squared plus 9, and then minus 3 squared, which is minus 9. So your plus 9 and your minus 9 cancel, and you just get t squared. So your t squared over t squareds cancel. That was the thing causing the whole problem. Now that's gone away. So this remaining expression, we can plug the 0 in for the t. So we'll get 1 over the square root of 9 plus 3. The square root of 9 is 3. So we're just going to get 1 divided by 3 plus 3, or 1 over 6. So that's what the limit's equal to. Okay. So that might be a little confusing just because it looks complicated, but we'll get more practice with that when we do the derivative. Yeah, a limit that does not exist. Well, with this 1 over x squared thing, we have some problems. Again, we have an asymptote at 0, but this one just keeps getting bigger and bigger and bigger. Basically, both asymptotes go to infinity. So if we look at the graph there, if we look at 1 over x squared, notice both sides go up. So as you go closer and closer to 0, the graph just keeps climbing higher and higher and higher. It's just going to go up and up and up and up forever and ever and ever. So for this reason, we would say that this graph has a limit that does not exist, but we can actually say that it goes to infinity because both sections are going to the same thing. Limit that truly does not exist, that doesn't go to positive infinity or negative infinity, would be 1 over the limit of 1 over x as x goes to 0, because your graph is going to two different things. So notice from the right-hand side, your graph is going up, and from the left-hand side, your graph is going down. So it's going to two different places. So that limit doesn't go to positive infinity, it doesn't go to negative infinity, it doesn't exist. So on Friday, we'll talk more about one-sided limits, and we'll look more at graphs than we did in the PowerPoint here. So again, that limit doesn't exist, but it does go to infinity. And then, yeah, so talking about one-sided limits. So probably we'll save that for next time. We'll actually look at some graphs, and I'll do more of this stuff by hand. One-sided limits just talks about which direction you're approaching from, because you can approach any x value from either the right or from the left. And a regular limit that we talk about means the limit from the right is the same as the limit from the left. Hence, it can be thought of as a two-sided limit. But yeah, why don't we call it a day with the end of this section. So I'm going to go ahead and stop the recording.